I am Dr. Basir-Ahamed-Khan, Assistant Professor of Physics, Krishnath College, Baharampur. I divide whole syllabus of kinetic theory of gases into three modules: Module 10, Module 11 and Module 12. There are two topics in Module 10: distribution of velocities of gas molecules and molecular collisions. Next, in Module 11, I will discuss the behavior of real gases. And then in Module 12, I will discuss on low temperature physics. Now, in Module 10, Module 10 is the distribution of velocities of gas molecules. Today, I will discuss on Maxwell-Boltzmann's law of distribution of velocities in an ideal gas, then mean velocity, RMS velocity and most probable velocity, the definition and its expression, degrees of freedom, law of equipartition of energy, only the statement of law of equipartition of energy, and specific heats of gases. And the next of module 10 is molecular collision. Here in molecular collisions, the subtopics are mean free path, collision probability, estimates of mean free path. In module 11, I will discuss behavior of real gases. The subtopics are deviation from the ideal gas equation, Andrews experiments on carbon dioxide gas, critical constant, continuity of liquid and gaseous state, vapor and gas, the difference of vapor and gas, what is vapor, what is gas, boil temperature, Van der Waals equation of state for real gases, values of critical constant, and comparison with experimental curves and PV diagram. And next in module 12, I will discuss low temperature physics. The subtopics are Joule's experiment, free adiabatic expansion of perfect gas, Joule-Thomson porous plug experiment, Joule-Thomson cooling, Joule-Thomson effect for real and Van der Waals gases, and temperature of inversion. Now today is the first lecture of module 10, distribution of velocities and Maxwell-Boltzmann law of distribution of velocities in an ideal gas. This is first lecture of module 10, Maxwell-Boltzmann distribution law. Let us consider an ideal gas at temperature T Kelvin. An ideal gas, consider an ideal gas at temperature T Kelvin. The molecules of the gas move at random in all possible direction with all possible velocities and collide with one another. Although due to the collisions, the velocity of a molecule changes with time. I repeat again, although due to the collision, the velocity of a molecule changes with time, but in the steady state, the number of molecules in a particular velocity range is independent of time. I repeat this point again. The gas molecules move random in all possible directions with all possible velocities and collide with one another. Although due to the collision, the velocity of a molecule changes with time, but in the steady state, the number of molecules in the particular velocity range is independent of time. And the law which gives This number is known as Maxwell's Boltzmann distribution law of molecular velocities. That means the number of molecules, Maxwell-Boltzmann distribution law gives the number of molecules at a particular velocity range is independent of time, and this velocity distribution law is known as Maxwell's Boltzmann distribution law. The Maxwell's Boltzmann distribution law is written as, suppose the velocity of the molecules in the range C and C plus dc, velocity range of gas molecules is C and C plus dc. Suppose if the velocity range of gas molecules is C and C plus dc, then Maxwell's distribution law gives dnc, the number of gas molecules in the velocity range C and C plus dc, dnc equal to 4 pi n a cube e to the power minus b c square into c square dc, where a equal to root over of m by 2 pi kt, and b equal to root over of b by root over of m by 2 kt. This is the value of the constant a and b, and the Maxwell's distribution gives the number of velocity in the range C and C plus dc equal to dnc equal to 4 pi n a cube e to the power minus b c square into c square dc, and n equal to number of molecules per unit volume. Number of molecules per unit volume. Molecules per unit volume. Per unit volume. This is the expression of Maxwell's Boltzmann distribution law. Here there is no scope to prove this formula in this lecture. That's why I put the expression or the number of molecules in the velocity range C and C plus dc equal to dnc equal to 4 pi n a cube e to the power minus bc square into c square dc. So since there is no scope in this video lecture to prove this relation, I just put the expression of Maxwell's Boltzmann distribution law. Now we want to calculate here the most probable speed, and if I plot this expression for a particular temperature, then I will get, that means dnc equal to 4 pi n a cube e to the power minus bc square into c square dc. Now I consider a new function fc equal to dnc divided by ndc, that is, it becomes 4 pi a cube 4 pi a cube e to the power minus bc square into c square, which is the fraction. It represents the fraction of total molecules per unit velocity range near c. fc represents it represents it represents the fraction represents the fraction of total molecules of total molecules fraction of total molecules per unit velocity range velocity range near the velocity c. So if I plot fc versus c, if I plot fc versus c, plot fc versus c versus c, then we get the nature of the function dnc, that is the Maxwell's-Boltzmann distribution law. So if I plot fc versus c, I will get the nature of velocity distribution. That means, suppose here this is fc and this is c and this is fc, and this is c. Then this expression fc versus 4 pi a cube e to the power minus bc square into c square, here this is a constant factor only, e to the power minus bc square and c square. That means these curves becomes like that. This is the velocity distribution curve of Maxwell's law. This is velocity distribution curve of Maxwell law, and this velocity is called most probable velocity. That means in this particular velocity the maximum number of gas molecules exist, and this velocity is called most probable velocity, and the curve or the plot represents the Maxwell's distribution law of molecular velocity. Now I want to calculate the most expression for most probable velocity by most probable speed. Expression for most probable speed, most probable speed, cm. This is most probable speed. I want to calculate the expression of most probable speed. That means the speed at which maximum number of gas molecules are exist in the system. Then from mathematics, from the maximum value of Fc, we calculate where ddc of Fc equal to 0. That means most probable speed, to calculate the most probable speed, I use the relation ddc of Fc, ddc of Fc equal to 0 when c equal to cm. This is the most probable speed relation. That means here we know that Fc equal to 4 pi aq e to the power minus bc square into c square. That means here, or we write here, 4 pi a cube e to the power minus bc square into minus 2bc into c square plus e to the power minus bc square into 2c equal to cm equal to 0, or 4 pi a cube is constant. Therefore from here we get minus bcm square plus 1 equal to 0, or cm equal to root over of 1 by b, or cm equal to, we know that b equal to root over of m by 2 kt. Therefore 1 by b means root over of 2 kt by m, 2 kt by m. This is the expression for most probable speed. This is the expression for most probable speed. Most probable speed is the velocity at which most of the molecules of the system move. That means most probable velocity means the velocity at which the velocity at which most of the molecules move in the system move most of the gas molecules moves in the system. Now we want to calculate the expression for average velocity or root mean average velocity and root mean square velocity. First of all, the root mean square velocity. Now we want to calculate root mean square velocity. Here it is defined as, we have dnc equal to 4 pi n a cube e to the power minus bc square into c square dc, where a equal to root over of m by 2 pi kt and b equal to root over of m by 2kt, m by 2kt, m by 2kt, m by 2kt, m by 2kt. Here root mean square velocity is defined as, it is defined as CRMS, CRMS, CRMS equal to root mean, first is root, then mean, then square velocity, 0 to infinity c square dnc, c square dnc. This is the relation of definition of root mean square velocity, and the limit of integration from 0 to infinity, because the velocity of the gas molecules changes from 0 to infinity. That means it becomes, if I put this expression here, it becomes 0 to infinity c square into 4 pi a cube, 4 pi n a cube e to the power minus b c square into c square dc divided by n. Therefore CRMS equal to CRMS square becomes 1 by n 4 pi n a cube into e to the power into integration over 0 to infinity e to the power minus bc square into c to the power 4 dc. Therefore it will become 4 pi a cube into I, where I equal to integration 0 to infinity e to the power minus bc square into c to the power 4 dc. Now using the gamma function, I get, now using the gamma function, we calculate the value of this integral. We get I equal to 3 by 8 b to the power 5 by 2 into gamma half. That means 3 by 8 2 kt divided by m whole to the power 5 by 2 into root pi. That is Therefore, CRMS square RMS square we get CRMS square we get 4 pi AQ times this. That means 4 pi AQ 4 pi A cube means m by 2 pi kt 2 pi kt whole to the power 3 half into 3 by 8 into 2 kt by m 2 kt by m whole to the power 5 by 2 into root pi, and it will become 3 kt by m 3 kt by m. Therefore CRMS equal to root over of 3 kt by m 3 kt by m. This is the expression for root mean squares velocity or root mean square speed. So I get two expression. Here is the velocity of most probable speed or most probable velocity, the velocity at which most of the molecules of the system move, and here we get the root mean square velocity of gas molecule. Now I calculate the average velocity of gas molecules. Average velocity of gas molecule. Now the average velocity of gas molecule, average velocity of gas molecule, average velocity of gas molecule, average velocity of gas molecule. Now average velocity of gas molecule is defined as equal to 0 to infinity CDNC divided by n, or 1 by n into integration over 0 to infinity 4 pi n a cube e to the power minus b c square into c square dc. That is it becomes 4 pi n a cube 4 pi n a cube 4 pi n a cube divided by n into I, where I equal to integration over 0 to infinity e to the power minus bc square into c cube dc, bc square c cube into dc. Now again I use the expression, I use the relation of gamma function. So using gamma function we change the integral into gamma function and we get I equal to 1 by 2 b square, 1 by 2 b square into gamma 1 equal to 1 by 2 b square, 1 by 2 b square. That is, therefore C average equal to equal to 4 pi n aq 2m by 2 pi kt 2 pi kt 2 pi kt whole to the power 3 half into half 2 kt by m whole to the square. That means by simplification we get 8 kt by m into pi, 8 kt by m pi. This is the expression for average velocity, 8 kt 8 kt by m pi, 8 kt by m pi. So therefore we get this is the average velocity. So we calculate three different type of expression of velocities. First of all, the cm, most probable speed, equal to root over of 2 kt by m, 2 kt by m, root mean square velocity, equal to 3 kt by m, root over of 3 kt by m. Here is 3 kt by m, here is m equal to 2 kt by m. So therefore we get the three different type of velocity relation of gas molecules. Okay.